Rod Adams, thank you so much for finally coming on the Titans of Nuclear podcast. The original is here.
I'm not so sure about the original, but yeah, it's been a while since we've talked about doing this. What, a couple of years now?
Yeah, I mean, well, I got to say, when I first tried to learn about the nuclear industry, not knowing anyone, I was obviously just Googling around the internet. And one of the things that I found was this incredible resource that you had built up, a blog, your own podcast, just a tremendous amount of information coming from someone who'd been in the industry for so long and was just saying it like it is too. Just saying it like it is.
Well, one of the things I do sometimes, challenge people. I haven't really been in the industry for a long time. I was in the industry for a grand total of 3 years. But I've been around the technology.
So that's the distinction.
Since 1981 when I started.
Since your submariner times.
I started nuclear power school in September of 81. So.
Okay, so take me all the way back. As we do, let's go back to the beginning. How did you even hear about this school and this technology? I'll
start with how I learned that I was really interested in nuclear energy. I was 8 years old. One of the things I've lived the utility life forever because my dad was a utility engineer. So to me, the power company was always the good guy. Yeah. The power company was the guy who sent Santa Claus to the company party every year and got me an extra present. The power company was a place where we went and had these wonderful picnics on this beautiful picnic grounds at the Cutler plant in Miami. He worked for Florida Power and Light Company. It was cool.
What did he do? What kind of engineer was he?
He was an electrical engineer.
Yeah.
So he designed transmission lines and transmission substations.
Awesome.
So he was a supervisor of transmission substations when he retired. So the Cutler plant, was a place where I had good memories, but the Cutler plant was beautiful except for these two big smokestacks that stuck up in the air. And one day when I was 8 years old, so I'd been to a couple of company picnics already, Dad came to me and says, "Hey, Rod, we're building a new plant down near Homestead, and it's not even going to have smokestacks." I was fascinated by it. So that was the introduction to nuclear. And so
That's pretty amazing.
He taught, as his company built, he wasn't involved in the project, but certainly as a guy who was interested in the company. He was a guy who brought his work home all the time, always talked to me. He was an investor, and his biggest shareholding was in his own company through the employee stock ownership program. Yeah. So he cared. He was interested in what this new plant was. It was Turkey Point, 1967 was when I was 8 years old. And, the CEO of Florida Power and Light Company was an environmentalist who loved South Florida, loved clean air, clean water, loved the Biscayne Bay. And he, as a businessman in South Florida, I think about 1964, 65, there was a company that was planning to build a causeway across the Biscayne Bay to what's known there as the Upper Keys. There really are keys that are further north than Key Largo, but they're all undeveloped now. But this company was going to build a causeway, which of course isn't a bridge, it's a barrier that separates the bay into two pieces. He's going to build a causeway from Turkey Point, which literally enough is a point that sticks out to make it a shorter path to these keys. And he said, "I got to block this project somehow." So Florida Power and Light Company bought the land and started planning to build power plants there.
Wow.
How else but better way to block a causeway? Own the point that they're trying to jump off from, And then, of course, once they built the nuclear plant, they were able to protect another 5 miles worth of the shoreline because Turkey Point's got the most unique cooling system in the country.
What's the cooling system?
Seen from overhead, it looks like a big radiator. It's a bunch of canals. And it's 5 miles long, 2 miles wide, and it's these shallow water canals. So if you look from above, from a Google Earth shot, you got this little teeny power plant from the satellite view, and this 5 mile long, straight channels of canal that provide the cooling, because it all evaporates, and that's the evaporative cooling. But they don't take water from the sea and pump it back out. They just take this water in the channel. Of course, they have to make it up now and again because you evaporate too much, and you don't get enough rain. You have to put some more water in. But so you protected another 5 miles worth of coastline.
So as a kid, you had the very fortunate privilege of not only knowing how energy works and how electricity works in our country, the backbone of modern society, but you also knew about nuclear.
Yeah.
And
I visited power plants. I knew what coal plants looked like. I knew what oil plants looked like. We burned a lot of oil in Florida.
And you knew very early on, not just the environmental aspects, the positive environmental aspects of nuclear, not just from hey, we can displace a worse energy source, but you saw firsthand other ways that nuclear and people who love nuclear go that extra mile to protect the environment.
Yeah.
And I've seen that across all sorts of plants too. Anywhere you go, any nuclear plant you go to, they're always talking about like, hey, the local wildlife we protect. There was a endangered hawk that came by, and we made sure that hawk was doing great. It's like all these things. Yeah. It's incredible.
Well, most
amazing stewards of the environment, the nuclear community.
Right. And most nuclear power plants are built on pieces of land that have ecological value. They're in remote places. They're surrounded by wildlife preserves or on coastlines or whatever. I mean, and some of them are beautiful, the locations.
Yeah.
You look at the pictures of Diablo Canyon, or, I mean, even PSEG's plants in New Jersey are on an artificial island. And so I used to sail past them when I was doing a circumnavigation of the Delmarva Peninsula. You go right past these 3 nuclear plants that are right on the bay there. But the other one that I saw frequently was it's on the Chesapeake Bay, Calvert Cliffs.
Calvert Cliffs, yeah.
Yeah.
That's close by.
Well, it's close by to here,
yeah.
Sure. And I sailed out of Annapolis, so I used to go down and pass that all the time. Funny story, when I was in Annapolis as a married man, doing some family stuff. Anyway, I and my wife used to volunteer for a fishing tournament. It was where they were pulling in striped bass, and or known as rockfish locally. But the largest fish caught in the tournament almost always was caught right off the power plant.
Because they like the warm
water.
And
I know that because I was the guy that used to track the leaderboard. That was my job. I had decent handwriting. So when they brought the big fish and they'd say, "Where'd you catch it?" They'd say, "Off the power plant."
Yeah. How did this interest turn into a career? You joined the Navy?
Well, sure. In high school, I figured out pretty quickly that I wanted to be an engineer. I wanted to learn about nuclear energy, and I talked to my guidance counselor. I had a really good guidance counselor. He happened to be a blue and gold officer for the Naval Academy. And he said, "Hey, you want to study nuclear engineering? The Navy's got the best nuclear program in the world, and they have this school that you can go to for free." College for free?
Yeah.
Now, dad and mom, had some savings and they put it away, but I was one of 4 kids.
Yeah.
And if I could help them out by figuring out how to go to college for free, that was a positive. So I talked to the guidance counselor, and I found out the Naval Academy and learned more about it, and wrote my high school yearbook. I was going to go into the Navy to become a nuclear engineer.
Amazing.
And yep. Then I took a little detour, tiny detour. I got to the academy.
Yeah.
And I met the engineering professors. Then I met the English professors. And I decided to be an English major.
Uh-oh.
Yeah.
How did that happen?
Well, the engineering professors were fairly typical engineers who talked about how difficult their major was and how much work I was going to have to put in to be able to even just pass their courses. And I said, "Well, what am I going to be learning about?" And that they couldn't answer that question. They said, so during the orientation, I went to the English department. They said, "Hey, You can study anything at the Naval Academy because all of us have this core curriculum.
Mm.
You know, I ended up as an English major with 2 years worth of calculus, so that was what 10, 12 semester hours or something like that. A year of physics, a year of electrical engineering, a year of chemistry. You know, all that stuff was all part of the core curriculum.
Mm.
English was an opportunity to do some reading, take some electives, to get involved in conversations, to learn how to communicate in writing and speaking. And so I thought that was a better way to get started in a naval officer career and have the opportunity to learn about nuclear later.
And then, so when did you come back to it?
Well, at the end, at the third year at the academy, you have to make a service selection. You have to decide whether you're going to drive ships around or fly airplanes or go into the Marine Corps or go into submarines. And submarines was the way to be a nuke, so I went and applied for nuclear power school, submarine program, had to go through an Admiral Rickover interview.
And when you say an Admiral Rickover interview, you mean with the actual Admiral Rickover?
Oh, yeah. Admiral Rickover was an 81-year-old man in 1981.
Holding on to his position for your life.
He was still on active duty, never wore a uniform. He's still on active duty, still operating out of the same little office and steel-issued desk that he'd always used. Had some decent decorations in his office. It was very bare, except for the mementos of ship launchings and stuff like that. But he was still there. He's still sitting there.
What do you remember about that interview specifically?
I remember almost exactly word for word what happened because it was a very short interview. I walked into his office. He says, "Adams, huh?" Kind of grumpy old man. And I said, "Yes, sir." He said, "Looks here like you were an English major." "Yes, sir." "Why were you an English major?" "Well, sir, I like to read and write." "Read and write, huh? You ever written any books?" I said, "Not yet, sir." And he looked at me and says, "I've written 3 books and I wasn't an English major. Have you ever read any of them?" Of course, the answer to that was, "Not yet, sir." I've read a couple of them since. I do have one of his books on my shelf. It's called Education in America or something like that. A fascinating book on public education in the 1950s.
Wow.
And what his recommendations were for making it better.
Wow.
But that was about the duration of the interview. He turned around to the captain who followed me as sort of my escort or mentor. He says, "What do you think, Captain, an English major?" He says, "Well, sir, I was an English major for the first 2 years of my college career." And that was the end of the interview. I walked out. They said, "Yours accepted."
Awesome. So you get into the program. What do you learn when you get there?
Nuclear power school starts off with some very fundamental math, science, chemistry stuff, math, physics, and chemistry. You take calculus all over again in about 6 weeks total. So you work fast, you work hard. Same with chemistry and physics, but it's focused chemistry. It's water chemistry because water is the big thing that we had to worry about. So you learn about corrosion and corrosion prevention and all those kinds of things. And then you got into some operations. You'll learn how to draw systems. You do all that stuff. It's pretty well. It's a very well structured training course. They've been refining it since 1950s. I guess 1953 is when it first started up. They initially held it at college campuses and eventually consolidated. But it's always been a 6-month course. And then at the end of that 6-month period, you go to a land-based prototype, which Navy lingo just means an operating reactor that is similar or identical to a shipboard reactor of a various type. Not every reactor type we had on ships had a prototype, but a fair number of them did.
Where was this? Where was this prototype?
My prototype was in upstate New York in a place called Boston Spa. And the prototype I went to was known locally as the Big Ball because it was the D1G prototype, which was built inside the containment dome or containment ball that was originally built for the Seawolf class submarine. And because Seawolf was a sodium-cooled intermediate spectrum reactor, they calculated they needed a very large containment to hold the pressure that might develop if sodium got mixed with water and had an explosion. So this big ball, and because the big ball was built and it's a big piece of concrete and steel lined, all that stuff, they reused it.
Interesting, because one of the things that I often hear the advanced technology companies, specifically in the sodium sector, say is that, hey, ours is going to be cheaper because we don't need all this extra containment stuff because we're a not pressurized system. But it seems to me what you're saying is the Navy thought differently.
Well, remember, the Navy is designing reactors that are going to be surrounded by water. So every reactor design, the designers have to go through what's the worst case scenario, what's the potential avenues, and what are the consequences of things happening. A land-based sodium-cooled fast reactor doesn't have to make the assumption that the reactor gets surrounded by water and the systems break and the sodium leaks out and it explodes. You don't necessarily have to do that if you're a land-based fast reactor, because there are ways to prove that there's no way that water can mix with your sodium except in a little smaller amount. And so you calculate what the maximum pressure would be if you have a tube rupture in your steam generator or whatever, and you have a different worst case scenario.
So why did the Navy then have such a large containment?
Well, because the worst case scenario on board a ship is that the ship sinks and implodes, and water does surround your entire system and collapses and have a big explosion.
I see.
Now, but you're building this thing on land,
yes,
and you want to protect the local population for the possibility of this explosion, and yet you have the same kind of design as you do on your ship. So they designed it as if this maximum case accident could happen even on the prototype.
Do you think that new nuclear reactors of the sodium variety are also going to need to have such protection?
No, because they're not going to the reviewers, and of course the Navy reactors have always been reviewed independently. That's little known, but not classified fact about them. The AEC or the NRC always had a group that reviewed naval reactor designs and gave their independent stamp of approval. But so even back then, they had this design that they were saying we're going to put on ship, and they say, well, you got to be able to withstand this. So how are you going to prove that you can withstand it on land without contaminating the local population? And so they built this big containment.
So what happened after your training there?
Went to the first ship, USS Stonewall Jackson, operating out of Kings Bay, Georgia. Did 2.5 years there, had 3 or 4 different junior officer jobs. Was initially the electrical officer, then I was the main propulsion assistant and the chemistry and radiological controls officer, and went forward for a while and was a communicator for a year, but I still stood watch as an EAL. Was taken off my first ship a little early because there was an immediate billet that the Navy had to fill at the Naval Postgraduate School. The guy who was in charge of submarines on the East Coast had made it one of his, ideas for improving the submarine force. He was going to get more nuclear trained officers to be able to go to graduate school. At the time I joined, submarine force had always been very busy. Nukes had always been very busy. Their career paths were packed. Nobody ever had any time to get a graduate degree because there was no time on a ship to study after hours because there was no after hours. And the land-based assignments that people got were pretty intense. And so anyway, he got 60 billets at the Naval Postgraduate School designated for submariners, and then he told his detailers, the personnel officers who do assignments, and said, hey, I got these billets, you better fill them. So there was a billet that was not being filled. They looked on my preference sheet and it said that I wanted to go to postgraduate school if there was an opportunity. They said, hey, how would you like to go? I looked at my CO. He says, we got plenty of people on board. You can leave if they need you. Darn, got to get off the ship 6 months early, go spend time with my family, go to graduate school. It was wonderful.
And what did you study there?
Systems technology.
What is that?
Well, the specific area of systems technology that I learned about was command, control, and communication systems. So this is 1985 to 87. Computers were a fairly recent thing. You know, the Macintosh personal computer had just come out in 84. You know, PCs came out in 81. So the Navy was had the PG school had a lot of work on computers, and of course the Navy had important communications challenges, particularly on submarines. We had the need to be able to bring together a lot of information and coalesce it and display it in a way that a commander could make rapid decisions.
And you have communications challenges on submarines because you can't maintain a link to the outside world. Is that the issue?
Well, radio waves don't travel underwater.
Right.
I mean, that's you can, but you have to do certain things to do it. So I don't talk much about that.
Yeah.
It's one of the few graduate degree programs I've ever heard of where one of the entry criteria to get in was having a TS SCI clearance.
What does that mean?
Top secret, special compartmented information.
Wow.
So
you study that and then...
Studied that, but you know, there was also a lot of general stuff, general engineering and a whole way of thinking about things in a systems point of view. It's not just individual components, but how do they come together to build a system? Of course, part of that is the human-machine interfaces, and that's part of the whole system, because what good is a perfect fire control system if nobody knows how to operate it and can't direct the weapons? And you know, so finished the PG school, went back to go through the department head school for the Navy, and then went to be the chief engineer on the USS von Steuben.
What kind of ship was that?
It's a SSBN. My first ship was also an SSBN.
What does SSBN mean?
Submarine.
Okay.
Ballistic missile. So SS means submarine. USS is normally a United States ship, but it also is United States submarine. And then the B was ballistic missile, and then BM.
And
ballistic missile, and then the N was nuclear. So the submarines that weren't nuclear are SS, and the submarines
when you
that
say
we use
nuclear or not nuclear, aren't they all nuclear powered?
Well, now they are, but they weren't always that way. You know, Jimmy Carter served on an SS, a diesel-powered submarine. He was an engineer of a diesel-powered submarine.
How long can those guys stay underwater for?
Well, they generally stay underwater a few hours at a time.
That's it.
And then they come back up and run their diesel engines with a snorkel out, or they come to the surface and run their diesel engines to recharge their batteries and then go back underwater. Now, they typically spend a few hours at a time underwater. They could, if they were very, very careful with their electrical use and they didn't try to go very far very fast, they could stay underwater for up to 24 hours at a time. That was the U.S. designs. Now, there are some diesel submarines operating in the world today that claim the ability to stay underwater for 48 or 72 hours, but they're not doing very much while they're there. They're not operating very much equipment. They're, not moving around at all. They're not patrolling. They're not expending battery by propelling the ship.
As compared to a nuclear submarine, which can stay underwater for months at a time and have all the power it needs.
Go as fast as it wants.
Get around the world, all underwater.
Right. I mean, we had a submarine that went around the world submerged as a demonstration. It was the guy who wrote the book about it was Ned Beach, who was the CEO of that boat. It was a special boat called the Triton, Triton, Triton. But that boat was one of the very few submarines we ever built that had 2 independent reactor plants. And so that was kind of a special thing.
So as the chief engineer, what was under your purview? Was it everything ship, everything nuclear, and everything missile?
No. I was the head of the engineering department. So I owned everything involved with the nuclear plant, the steam plant, the whole ship's electrical system, the ship's ballast system, the part of the system that allows us to control the ship, the hydraulics, the sanitary systems, the poop, the showers, all that stuff. That was mine. Let's see, atmosphere control equipment. So the carbon dioxide scrubbers, the oxygen generators, which some people, probably these days would really want to call them hydrogen generators.
Mm.
But we threw away the hydrogen. We didn't want that stuff around. It's too explosive.
Mm.
But the oxygen we needed because us, human life forms on board were using up some oxygen as we were going through our day, and you had to put some more back into the ship. So we had an oxygen generation system that took pure water, put electrodes through it and separated the hydrogen and the oxygen. So all that stuff was under my purview. I had 5 division officers working for me, 5 chief petty officers or 6 chief petty officers, whatever it was. And then a very senior enlisted who was my assistant engineer, essentially.
And then who ran
He was a
the
master
nuclear core itself? What would their role be?
Well, the nuclear core and the reactor operation panel within the area was owned by the reactor controls division. So there was a reactor controls division officer, and I think he had about 8 people working for him. They were the reactor operators.
And then you guys interface where the steam is created, essentially.
Well, it's an integrated system. The guy who's the engineering officer watch is in charge of making the heat and producing and controlling the steam flow. So, we ran it with a very small group of people. A typical watch section was 15 or 16 people.
And sorry, what does the word watch section mean?
Well, ships run all the time.
Mm-hmm.
So no human could keep up with the power plant. So we had 3 different sections of people that could stand a certain segment of time.
I see, like 8-hour shifts or something.
Yeah, shifts, watch, yeah.
Got it.
Yeah. We did 8-hour or 6-hour shifts, did 3 of them. So we had a constantly rotating schedule because
yes,
we said the 18-hour day. It was, so sometimes you get really confused as what day it is.
No sunlight. It's got to be a mess down there.
It's not
Just
a mess.
just 100 dudes working on heavy equipment.
150 hardworking people whose entertainment was playing cards and watching movies and going back to work.
Any
reading books.
Any wrestling matches down there? Sometimes I see on
Nah.
you ever see on the TV shows where it's like 2 guys down there for so long they get frustrated, arm wrestling contest.
Oh, we had arm wrestling contests.
Yeah.
Sure. We had there was some interesting stuff going on, but most of what happens on a submarine stays on a submarine.
Okay, sure. We'll figure that out over beers later. How long were you the chief engineer for?
40 months, a little over 3 years.
And then where'd your career go after that?
I went after my engineer tour. I finally got the assignment I'd been wanting for a while, was to go teach at the Naval Academy. So I went to teach at the Naval Academy.
And what did you teach?
Well, actually, I ended up not teaching. I had an assignment as a teacher. Somehow during the transition time and my orders and everything, I got to the school and they told me, well, you're going to go work in this area because your billet got traded to the commandant, and so now you're going to go to pro programs. And anyway, as it turned out, I ended up spending the time as a company officer, which is, the senior adult in the room with 120 midshipmen, all very bright, very motivated, athletic college students, with the seniors having positions where they're in charge of everybody else, but every company has some adult supervision. And although I was fairly senior to have that particular job, just before my arrival, there'd been an incident where a company officer who wasn't very far out of the academy himself had improperly guided some people, and so they decided they actually turned it so it was every other company officer. So there was at that time 30 companies, and so about 15 of us were 04s, lieutenant commanders rather than lieutenants or lieutenant junior grade. So I did that for 3 years, but that job wasn't as fulfilling and as time consuming as the job I'd just come from.
Mm.
So while I was there, I started taking classes in alternative energy.
Mm.
And then after taking a couple of high-level engineering classes in alternative energy, part of it was I wanted to bulk up my engineering cred because I liked engineering a lot, loved it when I was chief engineer, but I was still a chief engineer kind of playing it in the Navy. People say, are you an engineer? Well, no, I can't claim to be an engineer because I don't have a PE.
I don't have PE either.
Yeah, but I don't even have a degree in engineering.
An engineer's an engineer. You don't.
No. Not when you want to. Anyway, so I took these courses to bulk up my engineering, and I got interested in an alternative energy that used nuclear fission as its heat source. So it was
an alternative energy.
Yeah.
That used nuclear heat.
Again, a backstory. When I was in graduate school, one of the things I did every day, or almost every day, was run along the Pacific Coast Highway. I had a running mate. He had been a ship engineer on a modern destroyer, which is powered by gas turbine engines. Gas turbines have a lot of neat features. They start up fast. You can replace the whole engine. You had 4 of them, so you had redundancy, but you could install an engine and whatever in 48 hours. It's all these neat things, but they burned a lot of fuel.
Mm-hmm.
And so we used to trade back and forth. Well, I liked being engineer on a gas turbine because everything was so much easier. I didn't have to maintain a steam plant, and my guys got to go to the beach. And of course, being an engineer on a steam plant, even if it's a nuclear steam plant, it's a pain in the butt. I mean, steam is a useful phase of water, but it really wants to get out of the pipes because it's under pretty high pressure, and it would prefer to expand and become water again and all that. So you had leaks, and you had special requirements for doing maintenance, and you had to keep inspecting the pipes to make sure there wasn't rust, and it was a lot of work. And there's a lot of tanks, there's a lot of big valves and motors and pumps and all that stuff, all associated with steam. And Mike would show me pictures of his gas turbine engine. It was a compressor, a combustion chamber, a turbine, and an intake and an exhale, and that's it. There was nothing else. There was, of course, some lubricating and all that stuff, but that was it, though. The whole system, and it was, maybe 40 feet long to be a 25 megawatt propulsion unit. I went, phew. And it's, 4 feet, 5 feet in diameter. So anyway, my alternative was, what if you could combine the best features of nuclear with the best features of Brayton cycle gas turbines? I said, man, that'd be so cool. You could have this engine that didn't need to be refueled. And of course, my buddy said he loved to do underway refueling. It was a real challenging time to be an officer of deck. But I said, hey, Mike, I'm a lazy guy. It sounds like a real dangerous time to be an officer of deck to me. And hard work, and you got to train everybody. He says, yeah, but they're so much fun. Fine, you go ahead and keep refueling every 3 days. I'll operate on a ship that can go for 12, 15 years at a time without refueling, and you'd be happy your way and I'll be happy my way. But anyway, so I wanted nuclear gas turbine. So our library had an automated or a computerized card catalog. This is 1990, early 1991. And I went in and typed in nuclear and gas turbine, green on green screen, beautiful stuff. Nuclear, and I came up with this whole bunch of hits. And apparently, but a lot of people had talked about nuclear gas turbines. It was in the 1950s, they were identifying it as, hey, that's kind of the ultimate. Because a Brayton cycle gas turbine loves a steady source of heat. One of the challenges in a combustion gas turbine is keeping the flame going. Say it's easy, but when you're changing power, it's hard to make sure you got fuel flow and gas flow balanced, and the flame stays, you don't flame out, and all these things that happen when you're talking about a turbine type engine. Whether it's an aeroderivative gas turbine on land, or whether it's a jet engine powering an airliner, or even a turboprop engine, which has got a turbine keeping that flame low. So they said, hey, nuclear's like steady heat, runs all the time. You can throw the gas through it, and we can even close the cycle. We could take the gas from the turbine, go through a cooler and go back in. So that way we could pick the gas we're using. We don't have to have combustion products.
Are there any closed cycle Brayton turbines that are commercially available now?
No.
Because I imagine it would also present a unique set of materials challenges.
Well, there's a unique set of materials challenges if you try to use combustion heat with a closed cycle Brayton. Now, there have been prototypes of that. The Germans built a 50 megawatt plant that used like waste coal in a furnace and had tubes going through it to heat the gas, and the gas was helium, and they were able to generate electricity. And for a time, that made sense to them because they didn't have any external sources of oil, so they were going down this path of burning dirty stuff that was cheap and, powering a gas turbine. But those issues and complications, and it turned out there was easier ways for them to make power, so they sort of abandoned that. The U.S. built a nuclear-heated, closed-cycle gas turbine mobile reactor, ML1. So it's a mobile low-power reactor, number one, fit in 2 boxes, each roughly the same size as a 20 TEU container. And one box would be on the back of the truck, and the other box would be pulled on a trailer. I've got video of them pulling this thing, driving it into an airplane.
How much power did it produce?
Well, it was designed to produce 300 to 500 kilowatts. This was in the early 1960s when Brayton cycle gas turbine technology was still relatively new. There weren't that many off-the-shelf units you could go buy or build or whatever. People weren't even using it for power generation because they were still too fuel inefficient at that time, because they still hadn't refined the manufacturing and get the tolerances right. So the ML1 project couldn't find an off-the-shelf turbine and compressor set that met their needs, their perceived needs. And so they decided to go buy a compressor, then go buy a turbine, and to match them up, and they didn't do the calculations right, and so it was a mismatch. Bottom line is they could never produce more than about 180 kilowatts. But it did produce power. It worked. It ran. It had some issues to testing, but hey, it was really a first of a kind, first ever anywhere. It ran for a few hundred hours before they.
And so you were collecting all this research on previous attempts to have a closed cycle Brayton nuclear powered.
Yep. And then turbine. I came up with ways to go better. Applied for and got a patent on a control system, and eventually left the active duty Navy to form a company called Adams Atomic Engines. And we were going to build small, deployable, manufacturable nuclear gas turbines, because it was so much simpler than the steam plant, and we were planning to go power islands and ships and those kinds of things. Bottom line, I'd say that we're about 20 years ahead of the cutting of the leading edge. That company was founded in 1993. We closed it down in 1990. Well, we put it to heavy sleep in 1996. Couldn't find any investors. The price of natural gas from 93 to 96 went down by a factor of, went down by about 75% over the course of that time, from about $4 a million BTU to like $2.30 when we first closed it. And by the late 90s, it was down to $1.80 a million BTU. We discovered coal bed methane, as was a big thing. People thought natural gas was cheap and going to be cheap forever. So nobody was really interested in investing. I didn't have that much F&F, friends and family money. We had some. We burned through most of it, and then decided that we'd stop burning money and let everybody go back to work and take care of business and see what could develop. I got recalled to active duty in the Navy in 1999. Well, before that, I ran a small manufacturing company for about 3 years, and that didn't work out, and decided to go back in the Navy.
So, Adams Atomic was your first attempt at a nuclear startup. You would join another nuclear startup later as well, the Empower Project.
But yeah. Now, and one thing I guess it's relevant to today is as one of the things that I took out of Adams Atomic Engines was we had come up with this publication that we were doing to try to help people understand more about what we were doing. And the initial version was called Atomic Energy Insights. We quickly realized that AEI was already taken as a 3-letter acronym by an organization that we didn't really agree that much with. So we changed our name to Atomic Insights.
That's great, and that's the origin of your website and your web presence now.
Yeah, the was a paper publication. It got put online in the early days of the internet by a college student who's now the head of nuclear energy for the NEA. Name is Sama Bilbao. She works
Sama, yeah.
So Sama was the college student who
I didn't know that.
Turned
what a great
Atomic Insights
into
there. HTML.
That's amazing.
Yeah, she told me, "Hey, Rod, your publication is great. It needs to be on the web." I was an old guy, 19. I graduated college in 81, right? So this was 1995, 96. What's the web? Anyway, so.
Yeah, Salmon's great. I can't wait to get her on the show as well. She's out in Paris right now, I think.
Yeah, she's a terrific ambassador for nuclear, but also a very talented engineer, very talented manager. She built a really good program at VCU, from scratch. Yeah, she's good.
Yeah.
Good people. So anyway, so Adams Atomic Engines, eventually just went away. We closed it completely in 2010, but that was when I was getting ready to take a position with the Empower Project.
And how did they find you, and what role did you take?
They found me because I had been beating on B&W's door to try to supply fuel for the Adams engine. And so I knew several of the people. I made some tours of their site. In the early 2000s, we tried to revive Adams Atomic Engines again, and we were actually making good progress. We started to have good conversation with some very high capacity capitalization folks. Spent New Year's Eve on the New Year's Day and the day after New Year's in New York City in the offices of Merrill Lynch in 2008. Great meetings, but you know what happened in summer of 2008?
Collapse.
Yeah. So, and Merrill Lynch went bankrupt, right? Who would have thought that would happen? So, anyway, during that period of time, trying to revive Adams Atomic Engines, I was still on active duty and doing stuff on part time and using my Navy check to pay for things and savings and whatever. I met Jeff Halfinger because he was running the TRISO development program at B&W, showed me their manufacturing facilities and that kind of stuff. And I kept in touch with Jeff. I would periodically call him from an airport and say, hey, what can you do if we did this many fuel bundles or this many pebbles or whatever? So Jeff and I had a pretty good relation.
And what type of fuel was the Adams Atomic Engine going to be?
High temperature gas reactor.
So this is uranium that's clad in this TRISO configuration.
It's got layers of I call it coated particle fuel. The particular coating design that's almost through the finish line of getting approved by the NRC is this tri-isotopic coating, TRISO. And so it's coated with 3 layers of graphite and silicon carbide, and one of the layers is porous, so any gases that get generated goes into the pores and doesn't create a pressure on the silicon carbide. And anyway, it's a really cool fuel. And then the configuration I really like was the pebble bed, because it offers the opportunity for exactly the same fuel elements to power small reactors, medium-sized reactors, big reactors. You just throw more balls into the hopper, right? That's all it is.
And then that's what your turbine was going to be. It was going to be balls in a hopper and then some sort of fan that moves hot helium, I guess?
No,
Or what was the gas going to be?
another innovation for another difference in the atomic engines was helium is a typical gas chosen by high temperature gas reactor guys. Long history of why that is. But you can't use helium in a conventional turbo machine.
Why?
Because it's very light. It's only a atomic mass of 2, or no, atomic mass of 4, sorry. Atomic mass of 4, and it doesn't form molecules. So its molar mass is very small. It's only 4. Now, the specific heat transfer capability of helium looks really cool on paper because it's 5 times that of air. But that's on a per unit mass basis. Compressors don't move mass, they move volume. On a per unit volume basis, a mole of air is exactly the same same volume as a mole of helium, assuming the same pressure and temperature. So the mass of a molecule of air is 7 times the mass. Mass of a molecule of air is 8 times, roughly 8 times the mass of helium. But if you take out just the nitrogen part of air, it's got a molecular weight of 28. So it's 7 times as heavy as helium. So the overall volumetric heat transfer coefficient of nitrogen is actually a little higher than air. It's like 1.3 times, a little bit higher than helium, about 1.3 times helium.
So what were you going to use?
Nitrogen. Nitrogen is inert gas, works fine, lasts a long time, runs perfectly well, doesn't interact with the carbon, and that would allow me to use conventional turbo machinery because nitrogen, unlike helium, behaves just like air, surprisingly enough, since air is 80% nitrogen.
So one thing that I've always been a little bit confused by with these closed Brayton cycle turbines is how, so in a conventional open cycle gas Brayton turbine, you've got your compressor and that gets your normal air and it shoves it into a really small spot. And then you light it on, you add some fuel and you light it on fire all at that very, very small spot. And then that adds heat to your system and expands those gases. And as those gases expand, that's where you're capturing the energy. How are you getting your heat into, so why do you need a compressor in a closed Brayton cycle? And how are you getting your heat into that very small spot?
Well, first of all, the very small spot is a artifact of the fact that you're using combustion.
Yes.
And you're injecting
So there
fuel.
is no very small spot?
There's no very small spot.
Got it.
As a matter of fact, you still need to compress the gas because the compression is part of the Brayton cycle. You have to compress the gas. Then you take a compressed gas and you heat it up. And so you have hot compressed gas that now has a lot more energy. See, if you just compress gas and then you expand gas, it cools down.
Yeah.
Right? You get this, instead of having a nice smooth expansion.
Right. Well, you need to add energy to the system anyway if you're going to get energy
so
out.
You take this compressor.
Yes.
And you compress the gas into a big space.
Okay.
Filled full of pebbles, in my case.
I see. So you're literally putting the pebbles in between.
It is the pebble bed reactor takes the place of the combustion chamber.
Got it. And you can still use, if you're breaking it up like that, you can still use standard off-the-shelf parts from a gas turbine?
You can. You very well could. But you could also use standard compressors and turbines, and you could have multiple compressors all filling this big space that's going to have some bleed off of high energy gas going and spinning turbines, a turbine, multiple turbines, whatever it takes. And so the system has a compression, a heating part, an expansion part through the turbine, and then a cooling part.
And is your compressor mechanically driven by the turbine as well? As it would be typical?
But more flexible is to have your compressors be electrically driven.
But then aren't you losing, if you're converting your mechanical energy to electricity, you've got your efficiency losses there.
Not really.
Okay.
Okay. If you have a shaft from your turbine, your power turbine, and part of the shaft energy is turning a compressor, you don't really have much gain there compared to having that whole turbine turning a generator and then using a wire to move the energy, the power into a motor. There's some, but not much. The electrical motors are pretty efficient. Right. And it allows you to decouple it, which gives you a lot of advantages compared to having, in terms of layout and some safety things and whatever, there's advantage to making it separate. So there's lots of off-the-shelf compressors out there.
So what were some of the challenges then that made investors skeptical? Because it seems to me you've got the whole system mapped out. You obviously put a lot of work into it. You obviously had a lot of experience with these types of systems. You couldn't come up with cost estimates plus minus 20% and then show it to an investor and be like, hey, listen, we're cheap.
I could not come up with a cost or schedule estimate for getting approval to do this.
I see. So come back to regulations.
Yeah. And although there are some people say, well, just go find another place to do it, I'd say, first of all, I'm an American. I have a family. I have a place where I like to live. I have no intention of living somewhere else. And, and partly because I wanted to stay married. So my wife wasn't interested in moving overseas and being away from her parents and away from my parents,
But this kind of system seems more like a product you would sell. I mean, Bill Gates, when he sells Microsoft around the world, he sells a product around the world. He doesn't have to actually go to these places. I mean, he does for like high-level business conversations.
Right, but you would do, if you were building the first of a kind, you would have to spend a lot of time there. I
see. So this wasn't one of these modular systems. This would be would be a full power plant that would be constructed from ground up somewhere.
No, it would be eventually, once you built them, you would factory produce them.
Right.
The intellectual inspiration was the mobile low power reactor number one.
Exactly. That's what I was thinking when you said that.
Reactor in a box.
Right. So why not just make them here and ship them across the world?
Well, but I couldn't get a license.
Which license did you need?
I needed a license to be able to own and operate a reactor.
But wouldn't that be the customer's responsibility, and then you would just assemble it?
If you wanted to sell reactors, yeah, but I wanted to sell electricity.
I see.
Electricity is a wonderful commodity, and from a business point of view, it's a perfect commodity because your customers buy it without even thinking about it. They walk into a room and flick the switch. They turn on the air conditioner, they change the thermostat. They're buying it automatically without even thinking about it. And they can't store it up, and so you don't bump into your own inventory. You can't fill the channel, right? As the material, as your product is being produced, it's being consumed. There's no inventory to hold.
Right.
So it's a beautiful product. If you're the low cost supplier of a commodity product like that, that's a pretty good place to be.
Right, but there's always the intermediary. Your customer's always going to be the utility because you're not going to draw power lines as well and hook them up to your customers'
What power lines? Put the box next to my customer.
I see. So these would be industrial customers.
Industrial customers.
Electricity to.
Again, I also was interested in the shipping market. I was also interested in islands that have their own distribution systems.
But in any of these cases, why would you want to sell electricity to a ship? Wouldn't you just want to sell an engine to a ship? Wouldn't you want to sell a product to a ship and be like, all right, it's yours now?
No.
More capital up front. Selling electricity, you're investing and then you only get to recoup your capital over time. But if you sell the product, you get that capital immediately. It seems to me like the product is a better business model. And it doesn't have these licensing.
Well, no, you can't. You have to, under our construct in the U.S., and even though when I was doing this in the 90s, it was a little bit different construct because that was prior to the one-step licensing from the Part 50 52, or
Part 50 to Part 52.
Part 50, Part 52. This was, the two-step licensing. You had to get a license to construct, but you still had to somehow prove to your customer that they could, in fact, get through the process of getting an operating license, even if that was your model. And there was no path. There was no, I talked to the NRC, they say, well, you're being cooled by something we're not familiar with. Nitrogen, nobody had suggested that before. You're using these high temperature fuels, but although there'd been plenty of use of these high temperature fuels, the Germans had run a very successful program in their AVR, 21 years. They said, nobody really knows how to make that fuel anymore. We had this company out in California, General Atomics, and they made fuel, but heck, the taxpayers paid them to destroy their fuel manufacturing facility and turn it into a parking lot, decommissioning in the early 90s. And so that was already gone by the time I was doing this. And so there was no fuel supply. So there's lots of, if there had been still triso fuels being manufactured, we would have had a better shot. But there was no fuel. We couldn't get an estimate of cost. We had all kinds of good reception from investors, but every time they asked those hard questions is, okay, so what is it going to take to get to the starting line? As I remind, I'm doing some investing and advising these days, and I remind people who are talking to investors, say, you don't talk to them about how you get to a finish line, because you're just getting to the starting line of running an enterprise that, as you've pointed out, could in fact dominate the world's energy industry or energy supply. We have the capability. We have really cool fuel that makes power without consuming anything, consumes a tiny little bit, but it's fascinating, it's cool, it's neat, and it's much better than the competition. That pound of uranium that has the same energy value as 30 tanker trucks full of oil.
Yeah.
And the pound of uranium costs $30. But anyway.
Yeah.
So, and then we got some raise.
So you developed this relationship with Empower through your own...
Jeff Halfinger. And when Jeff became the project manager for the Empower reactor program, and I was getting ready to retire from the Navy, I called him up and said, hey, Jeff, you got anything going on? He says, I really need some help. And, I had some experience in the Navy writing procedures,
and building
processes.
Yeah, so what point of the project was that in at that point? How many engineers were there? What level of design was it at?
Well, they'd been going for maybe it had been about 2 years since I'd actually covered their announcement to the world that they were doing this.
And
as Atomic Insights, and my hobby while I was in the Navy, I went to their opening, and so they'd been around 2 years. And so in 2010, I joined the team, and we were probably a total of 50 at that point. So rapidly growing though.
So B&W, who was or still is a fuel, or I guess it's BWXT now, but I think it was all part of the same organization then. They were a fuel supplier to the Navy, had a ton of nuclear experience.
Fuel and major components.
Yeah, major components. And so this is...
Control rod drive mechanisms.
And so they decided that they were going to make what was one of the first small modular reactor concepts. Mm-hmm. And what was the whole thesis here? They were just going to make it cheaper? It was going to be a standard... What kind of fuel?
It was going to be a light water reactor. They wanted to
boiling
use
or pressurized or
pressurized water, but it was going to be an integral light water reactor, meaning that the steam generators, the pressurizer, all that stuff was going to be in a single vertical column, and all that was going to be part of the pressure vessel. Get rid of the idea of small break locas, that kind of stuff. It was a small modular reactor that was 85 feet tall.
And that's just the vessel. That's just the integral vessel.
Yeah.
And then it would have to be inside of a power plant structure of some sort.
Yeah. So there was some really good stuff that I learned there, some challenges. I don't really want to do any critiquing of the Empower project.
But we should, because that's what we got to learn from them. I mean, we don't have to badmouth anyone.
It's going to be a different show.
Yeah.
Because at this point, it's a wonderful topic.
Yeah.
But at this point, I've got a plane to catch.
Okay. All right.
No, Empower was great. I was there for 3 years. I learned a lot. Was the process and procedure development guy. So I wrote procedures. I read regulations all the time. Tried to comply. Had some interactions with the NRC. Sat in meetings. Those kinds of good stuff, and learned a tremendous amount. But after doing that for 3 years and continuing to write, I decided in 2013 to leave Empower. Part of it was I had read some handwriting written on a wall somewhere that said that the project was not doing well and was getting ready to be closed down. Turned out it happened about 2 or 3 months after I left that the handwriting became more visible to everybody, and the announcement was made, and a lot of that wonderful team of people that I worked with got dispersed to the winds. Some of them stayed with B&W. Some of they hung on to a lot of the talent that they brought in from that, but others ended up going to other places.
And then, where'd you go from there? So now, I mean, you continue with the podcast.
Yeah, I left.
You're working with the advising on funding startups.
That's a new thing, Nucleation Capital. Just started that. Didn't just start it. I started the groundwork laying and all that stuff in the relationship. Met the people that are the principals almost 18 months ago now. But for the last 18 months, we've been building team, getting legal and constructs, and a lot of early conversation with folks. And now we're building that organization as a clean energy supplier, a supplier of acceleration tools, capital, to people developing clean energy that will help avert the real climate crisis of exceeding targeted goals and all that stuff.
You said clean energy. Does that mean things beyond nuclear, or is it just nuclear?
No, we're unique in the clean energy field in that we have done a lot of homework, and we realize that doesn't matter what other people's definition is. If you've got objective criteria, nuclear can meet any objective criteria you have for what the energy system should be to be both friendly to the environment and able to build itself, to supply enough power to build itself and replicate itself and spread around the world and power people and those kinds of things.
And what do you look for in companies that you want to invest in?
Well, we're looking at companies that are beyond the seed stage, beyond early problems of team building and all that stuff. They need to have a good team in place, a strong vision for where they're going, but also the product pretty much developed. Maybe it's not approved yet, but they know what they're going to take to their wherever they're going to go, and they know what their steps are. They've got a plan laid out, and those are the kind of companies that are really ready for the next stage of capital raise, so that they've got the ability to build their factories, maybe build some early projects, got capital rather than having to go out and borrow money for the next project.
So there are only so many companies that meet that bill, and we all know who they are. I mean, there are probably only 10 or so, and they've all pulled in, probably 5, 10, 20 million bucks each. Already.
We're also interested in the suppliers and in the supply chain, and how are we going to put this all together? And yes, there's a limited, but there's enough variety that we believe it's time for a diverse portfolio of these companies is going to be interesting, rather than having somebody have to pick exactly which one's going to be the leader. We want to grow the whole industry. We want to attract more capital in the industry. We want to get several of these companies succeeding, and we think that we can add a lot of value by being there.
So based on your prior entrepreneurial experience in the space, and having worked for a startup in the space, and now looking at investing in some of these startups in the space, beyond the stage of readiness that their technology is, what would separate one nuclear company from another? How would you know if one was going to be successful enough for you to put capital behind it? Would
Well,
it be a market-based approach, technology approach? What would be?
well, part of it is what is the company's strategy for getting their product to the market and spreading the market, and what's their, how are they going to do this, and what's their plan, and have they designed a product that's ready for us, or are they trying to get funding to build 1,000 megawatt fast chloride salt reactor or something? Do they have something that's entry level that can be improved once they prove they can do the things that companies do? You got to have products you can actually deliver in a reasonable time frame.
So what size and technology would you look for?
We're focusing on advanced reactors and
so that means
small
advanced
reactors.
fuel cycles. That means non-light water.
No.
Okay,
No.
it means
No.
anything that's just not a Gen 2.
It's not well, first of all, it can't be a great big project. We're not going to be big enough to make any significant impact on an AP1000 project. It's just not in the cards at this point. But we can make an impact and actually accelerate somebody with, say, $40 to $80 million worth of money, and that's what it's going to take to get them into a really good stage. Those are the companies we're interested in. We don't want to buy anything. We don't want to be the owners. We don't want to control it. We want to have good management teams. We want to have people whose real next ingredient that they need to make their pot ready to boil is they need capital. That's the people we're looking for. And there are some of those. We believe there's some people that have lined up some great partners. They've lined up customers already. They've got half of what they need. They need the other half. Well, they've got 70% of what they need. They need the next 30%. So that's where we are.
So I know you got to run soon, but as we wrap up here, I'd love for you to just kind of, help our audience, just remind them why nuclear is so important.
Sure. Well, nuclear is important because people, society, had developed based on energy. When we could capture the energy and have, unfortunately, first we did it by having other people and animals do our work for us. That was the way you could get some real time to think and to prosper and to expand your mind a little bit and to have a comfortable life. Of course, it was only available to a very small number of people when it was other people doing all the work. The first captured energy that humans used were slaves, other people. And then you moved on. You could get machines to do things. You could pump out wells and move products around the world, and you could travel yourself. And anyway, we've always built on energy. Energy is important. Fuels are important. But cleanliness is important too. It's some people say we may have been wrong by going to coal under Jimmy Carter, but nobody thought about climate back then. Well, people think about air pollution. People are already thinking about water pollution. They're already worried about losing mountains and that kind of stuff, but they didn't think about that. They just were. So nuclear doesn't require much material movement, doesn't have to much material be transported from place to place. A kid with a backpack can carry as much as a moderately sized oil tanker. Just throw it on the back, fill it full of uranium, walk across the Gobi Desert, whatever you want to do. You get energy to where people are. I used to have this vision of having these reactors that I could get airlifted and put them in the center of Africa, and suddenly this village where the women spent all their days carrying twigs on their head to bring enough power to cook their meals at night would have water that could be pumped out of the ground, and they could have it, made available to them. They didn't have to go find twigs. They don't have to carry water. All the things that we have always taken for granted living here in the U.S., where almost every place you go there's a socket. That is important to me, to spread the wealth. And I did mission trips when I was a kid, and went to places where there was no power. And I know that go from places where there is no power to places where there are power. Huge difference in potential. Now, there's lots of places in the U.S. that are powered that are still desperately poor, but they've at least got half the battle done. They've got electricity. I remember when I was raising my kids, and I was living in base housing, and every Saturday for about a month they would turn off our electricity for like 4 hours at a time because they were doing some maintenance, and we'd take the kids out. But one day my little girl looked up at me and she says, "Daddy, I don't ever want to live somewhere where there's no power." She was 4 years old. But that's what nuclear can do. That, of course, it can also provide heat. It can provide motion. Ships are a great application for nuclear power. The world shipping industry is responsible for about 6% of the CO2 emissions every year, and about almost 50% of the sulfur emissions up until very recently. And only recently, within the last few years, have the sulfur limitations on shipboard fuels started to approach those of overland fuels. The shipping industry was the world's dumping ground for the sulfur that had been removed from everybody else's oil. The 15 ppm that we have on our road diesels in the U.S. used to be 300 ppm, but that sulfur has to go somewhere. Well, it always went to the bottom of the barrel, the shipboard fuel oil, which was allowed to be up to 20,000 parts per million sulfur. And that made it cheap. Now that they have to remove their sulfur too, and they got to find other markets for the sulfur, the shipboard fuels have like doubled in price. So the shipping industry is faced with that. They either got to install scrubbers, or they got to go slower, or they got to do something. And I think that they would love to do nuclear, but they're not going to put an unproven power plant on a ship. Got to come to the point where you've got a proven power plant. But nuclear is important stuff. And it's exciting stuff. It's fun. And it's also fun to be kind of an agitator in an industry full of people where conformity has always been, conformity and compliance have been the ways to go forward in this business for a long time. And I'm just not a conformist. And I don't like to comply all that much. Yeah, so.
Right, Adam, thank you so much.